Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to talk about the interval of convergence for Taylor series. So we've already seen how to generate Taylor polynomials and use them how to approximate functions in Mathematica. For instance, if I consider the function 1 over 1 minus x, then I can use the series command to find the 10th degree polynomial of that function centered at 0, and then I can use the normal command to clean up the output and store that result as a function. The result will have Mathematica generate the 10th degree polynomial. And then I can use that polynomial to approximate the function. For instance, if I wanted to evaluate my function at 0.5, I could approximate that value by evaluating the Taylor polynomial at 0.5. And I can see that the Taylor polynomial approximation is very close to the exact value of my function evaluated at 0.5. However, if I try that same technique to approximate my function at 1.5, here I can see that my Taylor polynomial is absolutely not a good approximation for the exact value of my function at 1.5. So why is this? The reason is because we can only use Taylor polynomials to approximate functions where the series converges to the function. So we have to look at this 10th degree Taylor polynomial, think about the series that we would get if we added the rest of the infinitely many terms, and then find out where that series converges. And then we can only use our polynomial inside that interval of convergence. So how do we determine where this series converges? Well, in this specific case, I can see a pattern from the terms of my series, which means I could write this in kind of a closed sum form, where the formula for each term is x raised to the n. I can test that hypothesis for my equation for the terms by using the sum command. If I use the sum command with this equation and I let n go from 0 to 10 to see the first 11 terms, I can see that really is a good equation representing this series. Now that I have a formula for the terms, I could use the ratio test to determine where my series converges. In that case, I'd want to evaluate my equation, my general term, at the n plus 1 term. So I would look at x raised to the n plus 1, and I would divide that by the nth term, or x raised to the n power. Then I would look at the limit of that ratio as n goes to infinity. And when I evaluate that, I get a result of x. And the idea is I know that whenever the absolute value of this limit of the ratio is less than 1, my series will converge. So that tells me my series converges when the absolute value of x is less than 1. So between negative 1 and 1, my series will converge, which explains why it's a good approximation at 0.5, but not a good approximation at 1.5. We can also view that same idea graphically. So here I have my function and my formula for generating the Taylor polynomials. And if I look at a plot of both those together, here I'm looking at the second degree Taylor polynomial. That's the orange curve, that quadratic function. I can see it's approximating the function 1 over 1 minus x pretty good in the interval maybe from negative 1/2 to positive 1/2. But if I increase the number of terms of the series that I use, now I'm using the 20th degree polynomial, now I can see it's a good approximation from negative 1 to 1, but it doesn't matter how many more terms I add, it will never be a good approximation out here at negative 1.5 or positive 1.5. It doesn't matter how many terms I use, I can only use the polynomial to approximate the function inside the interval of convergence. So what if I have a different type of series where I can't write a closed form equation for the terms of the series? Let's consider another example. We'll go back to showing two terms, and now we'll consider the function that is the natural log of the quantity 2 plus x raised to the 5th power. So now if we look at that function, I might look at the first few terms of the polynomial, and even if I look at maybe a few more terms here, now I may be able to find a closed form formula for that series, but I might not be able to. But whether I can or whether I can't, I can still consider this graphically. Looking at my graph here, I can see that my polynomial seems to be a good approximation from maybe negative 1/2 over to positive 1.5. But if I crank up my number of terms, maybe to 60, and understand that if I use a big number of terms, I might not want to show the output of my actual Taylor polynomial. But here I can see that I have a good approximation from x equals -2 to +2. And it seems that even if I crank that number of terms way up, that still seems to be the interval of convergence. You should note that we're just approximating the interval of convergence to be -2 to 2. It certainly could be -2.02 to +2.02. We're just approximating that interval graphically. Alright, this concludes this video on interval of convergence.